Hello everyone, in this video we will solve question number 1 on the topic of stresses and pore pressure in soils. So let us read the problem and see how we can solve it. We are given here a soil profile. So you've been given the results of a recent geotechnical exploration for a local project. The groundwater table at the time of exploration was 1.5 meter from the existing ground surface. So this is a groundwater table here. This is also the interface between the SC soil and the MH soil layers. These are symbols for the soils. You must have studied this in the soil classification chapter. So the figure below provides the soil profile at the time of the geotechnical exploration. From the provided information, calculate total stress, pore pressure, and effective stress with depth and plot them on the provided graphs. And you must label numbers on the graphs for full credit. So let us see the essential knowledge that we have to possess here. We need to understand the meaning of pore water pressure, effective stress, and total stress in soil. So when you have a pore water pressure, so the value is equal in all directions. In the general sense, when we talk about the soil or earth pressure itself, so you may have a vertical stress that's different from the horizontal stress. And these are the sets of equations that determine the different values of stresses. So sigma V is the total stress. In general, it is the effective stress plus the pore water pressure. This applies to the vertical stress, and the one below it applies to the horizontal stress. And also here, if we are talking about the in situ stress due to a profile of that nature, so basically we will have the total stress note here denotes the overburden pressure equals the effective vertical overburden pressure plus the hydrostatic pressure. And the same applies for the horizontal stress. So the solution strategy for problem of that nature is to determine the total stress, pore pressure from known formulas given the profile that we have here, and we then will use this to basically determine the profile. So we already mentioned the required stuff here. So let us start with point A. It is important for you to put a statement of that nature. This can be a clever way to help yourself determine the stresses. This says point A carries 1.4 meter of moist SC soil. That's SC soil. The first symbol refers to the primary soil. That's a clayey sand, and then the second here is just to add the notion of clayey part or fraction within the soil. So this point here, that's point A, it is carrying 1.5 meter of moist. Why we say moist here? Because the groundwater table actually is below the soil layer. So here you can see that point A is not carrying any water head. So then we substitute that in this equation the total vertical pressure over burden is basically whatever the soil is carrying, and we express it in terms of gamma H. So 1.5 meter is the column of soil carried at point A. 16.5 is the moist. Note here that I used the moist, not the saturated. The moist, that's 16.5, and this has given me 24.75 kPa. And U naught equals 0. Why? Because the groundwater table here coincides with the elevation of point A itself. And from the difference between the total stress and the pore water pressure, I determine the effective stress. Effective stress is sigma V naught minus U naught. 24.75 minus 0, that's basically 24.75 kPa. So now I'm done with the stresses at point A. I will repeat the same for all other points. Point B, let us put this statement. Again, it's very helpful for you to know what the soil point is carrying. So we're saying point B carries 1.5 meter of moist SC soil. So I'll talk about this point, that's point B. So it's carrying all this weight of this layer, which is 1.5 meter deep of moist SC, because the soil is moist. And it's also carrying 1 meter of saturated MH soil, because this elevation is 1.5, this elevation is 2.5. So point B is carrying also 1 meter of this soil, which is soil MH here, which is basically silt. It also carries 1 meter of water. Why? Because this is 1.5 here, 1.5 meter elevation, and this is the level of the groundwater table, 2.5 meters. So the difference is 1 meter. So I have 1 meter of water head above point B. Once you put a statement of that nature to remind yourself, you can then substitute and get the values. The total stress vertical here is basically 1.5 meter of moist. So I use the moist unit weight 16.5, plus I have 1 meter of saturated silt. So that's 1 meter times 17, because gamma saturated is 17. So the total pressure at point B is 41.75. Now to calculate the hydrostatic pressure, remember, it also carries 1 meter of water. So I would basically, well, here I basically substitute for the height of the water above point B, that's 1 meter. That's 1 meter here, times the unit weight of water is 9.8. So I have 9.8 kPa hydrostatic pressure at point B. Now subtract 9.8 from 41.75 in this equation here. Remember, always the effective stress is the difference between the total stress and the hydrostatic pressure. So 31.95. So now I calculated at point B the three values of the total stress, hydrostatic pressure or pore water pressure, and also the effective vertical stress. Repeat the same for point C. Let us see what point C is carrying. Some people may calculate this in a different manner by adding whatever the soil is carrying at point B, for example, everything above, and then when it comes to C, you add the column of soil between B and C. But it's a good idea actually to repeat this in case if you have done a mistake in the calculations above, you can still get some marks when you do this in the sense I'm putting it here. So sigma V naught at point C is basically you have 1.5 meter of moist soil, 1.5 moist, so I'm using 16.5. I have 2.5 meter of saturated MH, because this is 4 meter, this is 1.5 meter, the difference is 2.5 meter, 2.5 meter. Saturated unit weight is 17, that's 67.25. Pore water pressure, here it says it also carries 2.5 meter of water at point C. Where is this 2.5 meter coming from? This elevation here is 4 meter. This elevation here where the groundwater table is here, so the pore pressure here is 0, and it increases linearly. That's 1.5 meter elevation, so the difference between 4 and 1.5 is 2.5. So the pore pressure is basically the water head 2.5 times the unit weight of water 9.8 kilonewton per meter cube. Some people sometimes take it as 10. That's 9.8 is a correct value. It depends on what you are given in the exam or the assignment. It's 24.5. So again, to calculate the effective stress, you subtract the pore pressure from the total stress, 67.25 minus 24.5. So I have 42.75. So this point C here is feeling effective vertical or overburden pressure of 42.75. Now, let us repeat the same process for point D. So point D is carrying 1.5 meter of moist soil, that's 1.5 meter, carrying 2.5 meter of saturated silt, that's 2.5 meter for all this MH layer, and it's carrying 3 meter of SM soil. So all these 3 meter between level elevation 4 and elevation 7. It also carries 5.5 meter of water, which is the difference between elevation 7 and the elevation 1.5. So substitution here would be straightforward. So 1.5 times 16.5, which is the unit weight here, the moist, plus 2.5 meters times 17, that's 17 for the unit weight of MH soil, plus 3 meter times 19, which is the unit weight of the saturated again for the SM soil. And this is 124.25. Now, for the pore pressure, I have a column of 5.5 times 9.8, that's 53.9. So the effective overburden pressure is basically the difference between the total stress 124.25, take away the 53.9, so that's 70.35. So by now I calculated all the three stresses at the 4 points A, B, C, and D. So what remains is to draw all of these and put the values. So point A, if you can see here, 24.75, that's total stress. Pore pressure is 0, that's pore pressure, the red, and the effective is the green, 24.75. The same is repeated for every layer, for every other point here. Point to consider, I want you to see that because point B is within this layer, any values that represent point A, point B, point C, or anywhere within this layer, as long as the soil here is uniform and the pore water pressure or the hydrostatic pressure here is uniform, so you should have a linear distribution. So this part is linear, this part is linear, this part is also linear within the very same soil. Here, if you see this sand here, so also you connect here as linear. If you calculate any value in between, it should lie on the same line. So I hope to see you in the next video.